Hello everyone, I hope everyone is healthy and doing well. In today's lecture, we're going to cover section 5.2, areas as limits of sums. This section is, in a sense, auxiliary. What do I mean by this? You can actually skip this section and directly read 5.3, the definite integral. That can be done, but if you do that, what's going to happen is that when the author defines the notion of upper Riemann sum and lower Riemann sum in section 5.3, those definitions will strike you as weird at first sight. Like they would look as if they're not motivated. What this section is supposed to do is this section is supposed to motivate those definitions that are going to come next in the following section. Okay, so in this section we're going to learn about the notion of area. We're going to basically learn how to measure the area of a region in plane, and this might sound like a naive question to you, like measuring areas, but let me be clear, that question is actually more difficult than you think at first sight. Okay, so today's lecture will be focused on the following question. How do we measure the area of a region in plane? Okay, before answering this question, maybe we should focus on the easier question, which takes place in one dimension. How do we measure the length of something? For example, let me grab this tablet. This length is approximately like 0.25 meters. But what does that really mean? This length being 0.25 meters. What that means is somewhere in the world, there is an object which is declared to have 1 meter. I'm not saying that it's measured to have a length 1 meter. It is declared to have length 1 meter. So that's like the definition of a meter. I mean, there is, by the way, such an object. I think this is how a meter was defined in the first place. There was a bar which is in Paris, I guess, and it is the 1 meter. Okay, and when I say that this length is 0.25 meters, what that means is if I were to take that bar and put it on a number line, aligning and marking this endpoint as 0 and this endpoint as 1, after that marking, if I were to align this tablet with that bar so that their left endpoints are aligned, this endpoint of the tablet would correspond to the real number 0.25. Okay, that's what it means for this side to have length 0.25 meters. So why am I talking about such a basic thing? The reason is I want you to understand two things here. When we measure the length, first we have a we have a unit defined in terms of some object. Like we declare something to be of length 1 meter, and then we're assuming that when we move that object around, its length does not change, and we measure everything else with respect to that. Okay, now we're gonna try to do the exact same thing for area. So in order to measure areas of regions, we shall make the following assumptions regarding the notion of area. Okay, just like that a 1 meter is a 1 meter in Paris is my starting point to measure everything else. What I'm about to list down will be my starting point to measure areas of regions. Okay, so these are my assumptions, and without these, I can't really do much. Like mathematics, in its, like by its nature, it's different than all the other sciences. In other sciences, you do experiments. There's like a real world, physical world outside you, and you actually get data from that. In mathematics, you don't do that. What you do is you have your assumptions, you have your axioms, and from these you make deductions. Okay, you derive stuff by logical arguments, and then you obtain the consequences of those assumptions, which are your theorems. Okay, so the point is, in order to prove something, I have to assume something, and these are going to be my assumptions regarding the area. Okay, so the first assumption: the area of a region is a non-negative real number. Okay, so my first assumption about the area is that it's supposed to be something non-negative, like that's consistent with our intuition of the notion of area, so that's fine. The second assumption is that the area of a rectangle with sides with sides having lengths A and B is AB. Okay, with okay, I want to make this. I want to move this over here with perpendicular sides. Clearly, I'm talking about the perpendicular sides. So the area of a rectangle with perpendicular sides having lengths A and B is AB. So this is my assumption. So I'm assuming that if I have a rectangle with perpendicular sides having lengths A and B, the area of the rectangle is AB. This is my assumption. And the third assumption is that if two regions can be obtained from each other by translations and rotations, then they have the same area. They have the same area. And finally, if we split a region into a disjoint pieces, then the area of the region is the sum of the areas of the pieces. So the third bullet point says that if you have two regions and if one of them can be translated and rotated into the other one, then these should have the same area, okay? And this is also consistent with our intuition regarding the notion of area. And the last item is also consistent with our intuition. It says that if you take a region, split this into disjoint pieces, disjoint meaning that they don't intersect, they don't overlap. When you add the areas of these pieces together, you're supposed to get the area of the whole region, okay? And over here, I'm not necessarily assuming that you have you split your region into finitely many pieces. I'm also allowing you to split this region into infinitely many pieces, provided that you can name each piece by a natural number, okay? The technical term for that is like you having countably many pieces, but let's not talk about that because that's beyond the scope of this course. So if you split a region into possibly countably many. So it doesn't matter what the phrase and in the parentheses means. I'm just writing that so that what I write would be technically correct. So if you don't know what that is, you can simply ignore it, okay? So these are my assumptions. Okay, now from these assumptions, you can derive, today's lecture is going to be about the following. Just from these assumptions, I am going to derive the area formula for a disk with radius r. We are going to prove that the area of a disk with radius r is pi r squared just from these assumptions, okay? But before that, let me talk about some basic facts. So using these assumptions, one can show that the area of the triangle okay, let's suppose that you have a triangle with a side lengths A and B and the angle between these sides is alpha. You can actually show that this is a 1/2 AB sine of alpha. Okay, so you can do this. How? Well, I'm not going to write down the full proof. You can do this, but let me tell you how the proof is going to go. So if this is your triangle, what you're going to do is you're going to add a copy of this triangle, and you're going to glue it in such a way that it will form a parallelogram like this. So this will be alpha alpha, this will be AA and BB, and by the third assumption, this triangle and this triangle, they have the same area. So the area of this parallelogram is twice the area of this triangle. And then you're going to cut this a parallelogram. You're going to cut this parallelogram from here, and you're going to move this piece over here. Okay, so you're going to move it over here, so you will get this rectangle. Now this length is a sine alpha, so the area of this rectangle by the second assumption is the area of the rectangle is, it's going to be AB sine alpha. And now, by the third and fourth bullet points, the area of this rectangle is the same as the area of the parallelogram, but that's like twice the area of the triangle. So area of the triangle is 1/2 AB sine alpha. Okay. So just from these four assumptions, you can actually deduce this formula for the area of a triangle, and you can also deduce the usual formula like base length times altitude divided by 2 in a similar fashion. Okay. So that's that. I'm going to use that later. This is why I actually showed this. So we have that. Now what? But after making these assumptions, we can find the areas of well-behaved regions by now. So I told you that our aim is to measure the areas of regions, but that was not completely true. It turns out that we can't measure the area of every region. We can measure areas of well-behaved regions. What does well-behaved mean? I am not going to explain that because that requires me to teach you about basic measure theory, which is way beyond the scope of this course. So let me tell you the following. In reality, in general, not every region has an area. Not every region is well behaved. For you, every region that you're going to use in this course and the next calculus course, when you do double integrals, when you do integration, when you do whatever, those will be well behaved regions, okay? So let's take that for granted. Every region that you're going to use will be well behaved. They will have well defined areas, but in reality, this is not the case, but that's beyond the scope of this course. So you can ignore this comment and pretend that everything works out nice, everything is well behaved. Now, after making these assumptions, we can find the areas of well behaved regions by approximating uh, these regions via basic shapes from outside and from within. Okay, so once you make these assumptions, you can actually, if you're a well-behaved region, you can approximate you can find this area by approximating these regions via basic shapes, whatever those are, which I'm not talking about at the moment, from outside and from within. And what do I mean by this? Instead of trying to explain what I mean by this a yellow highlighted phrase, I'm going to show you what I mean on an example, okay? Example. Let us prove that the area of a disk, the area of a with disk with radius r is pi r squared. Okay, so we're going to prove that the area of a disk with a radius r is pi r squared. You probably know this fact since I don't know, fourth grade, fifth grade, I don't know, but I am pretty sure that almost all of you have no idea why this is true. Like your high school teachers or secondary school teachers, they simply told you that this is the case without providing you with a proof. And you've been exposed to this so many times that this looks as if this is a fact of life, which is the case, but it's not a fact of life because your teachers told you that this is the case. It's a fact of life because of the argument I'm about to describe. Okay, so let's prove that the area of a disk with radius r is pi r squared. And proof. So in order to draw my disk, let me first put a coordinate axis over here, a big one. Okay, xy. And let me let me put a circle here. Okay, let me center it. Okay. So pretend that this is x squared plus y squared equals r squared. So this is a circle with radius r. Okay, what I'm going to do is this. I'm going to pick an integer greater than or equal to 3, and I am going to set alpha to be 2 pi over n. Okay, and then here's what I'm gonna do. I am going to create a triangle here, where I'm going to create a triangle here where this angle is alpha. Okay, so this angle is alpha. Now pretend that I take copies of this triangle and I'm gluing them like this back to back. What is going to happen? You see, I chose my alpha to be 2 pi over n, which means that when I put n of these triangles together, at the end, I am going to get a regular angle, okay? A regular angle. Angle means that it's a polygon with n sides. Regular means that all the sides and all the inner, all these angles, they are the same, okay? Okay, so that's fine. Why am I doing this? Now, let me show you something that I found using Google. In this math application GeoGebra, someone programmed this. So in this, I have this circle, and in this circle, within the circle, we have an inscribed polygon with 3 sides. Now I'm going to increase the number of the sides. So I had a triangle. Now have a square, pentagon, hexagon, and it goes like this. I'm increasing the number of sides. As you can see, what is happening is the area of this polygon seems as if it is approximating the area of the circle. Now, I can't say that for sure at the moment because you see these these pieces which are my errors, they're like getting smaller and smaller. They're getting smaller and smaller, but the number of these pieces it's also increasing. Okay, so at the moment it's not for sure that the area of these the areas of these polygons are going to approximate the area of the circle, but it seems as if that's the case. Okay, so okay, that's that. So I'm guessing that this would be the case unless this is some kind of illusion. Let me actually show you that this is the case, and let me find the limit of the areas of these polygons. Okay, so now when I put 50 sides, you can't even see the difference, at least on not on the computer screen. Okay, so what I'm going to do is I'm going to create other triangles. This time what I'm going to do is, okay, so I'm going to extend these lines segments, and what I'm going to do is I'm going to put a line segment which is parallel to this guy and which is tangent to the circle. Okay, and then if you keep doing this, if you keep doing this, you will have another a another regular angle. Okay, so you have that. Now, from the third assumption that I made about, no, from the last assumption that I made about the notion of area, you can actually write the following down, not just from the last assumption, but using all the assumptions that I made about the area, the notion of area, you can actually write the following down. The area of the blue polygon, the blue angon, is less than or equal to the area of the circle, sorry, the area of the disk, the area of the disk with a radius r, and this is less than or equal to the area of the green polygon. Okay, now let me find these areas. Okay, what is the and let's pick this color. What is the area of this blue triangle? Okay, what's the area of this blue triangle? It is from the formula that I derived over here. It is a 1/2 times. You see, this side is like this length is r, so and the other length, this side has length r, so it's like 1/2 r squared times sine alpha. Okay, and how many such triangles do I have in this polygon? Like this polygon is made up from n triangles like this. So the area of the blue polygon is n times the area of one of these triangles. Okay. And what's the area of the green polygon? Now, this green polygon is again made up of n triangles, each of which has area. Now let's compute this. What I'm going to do now is I'm going to draw this line segment. And this is going to bisect the angle, so this is going to be alpha over 2, alpha over 2. And okay, it's not, well, this length will be here, it's going to be r, okay, because this point is on the circle. So this is going to be r, which means that this length will be r tangent of alpha over 2, okay? And these are equal to each other. So what's the base length of this green triangle? It's 2 times r tangent alpha over 2. What's the altitude? It's r. So from the usual area formula for a triangle, I have 1/2 times base, 1/2 times base times altitude. So I have that. Now, what I'm going to do is, remember, when I increased the number of sides of this polygon, the area of this the areas of these polygons seemed as if they are increasing up to the area of the disk. So I'm going to take the limit of right hand side and left hand side as n goes to infinity. Now, by taking the limit of all sides as n goes to infinity, we get that. Now, let me take the limit of the left hand side. N times 1/2 r squared sine of. Now, alpha, remember alpha is equal to, alpha is over here, it's equal to 2 pi over n. So this is 2 pi over n. Now, what I'm going to do is, I am going to rewrite this as follows. Sine 2 pi over n divided by a, I am going to divide and multiply this by pi, and I'm going to write this n over 2 as 1 over 2 over n. So I am going to have this. And I have r squared here, okay? Now, if you think of a this term here as your t, you'll see that this limit is the same as limit of sine t over t times pi r squared as t goes to 0. And you know that this limit goes to 1. So this limit is going to be pi r squared, okay? So the limit of the blue expression here, the limit of the left-hand side is pi r squared. Okay. Now, let me take the limit of the right-hand side. A and 1/2, and and 1/2 2r tangent of alpha over 2 times r. So let's cancel these 2's, and let me rewrite this as a, now instead of alpha I write, remember what alpha is, it's a 2 pi over n. So I'm gonna have a tangent of pi over n here instead of this term, and I'm gonna write a, instead of n I'm gonna write 1 over 1 over n, and I'm going to divide and multiply by pi in order to be able to do the exact same trick. Okay, and then I have r squared. And now, by doing the exact same trick, you can get that over here I see the limit of tangent t over t as t goes to 0. By L'Hopital's rule, you can prove that that limit is 1. So this limit, well, this limit will be 1. So you get pi r squared. So the left hand side over here goes to pi r squared, the right hand side over here goes to pi r squared, and the quantity squeezed in between, it's independent of n, it's a fixed number. So by squeeze theorem, it has to be pi r squared, okay? So by squeeze theorem, we get that the area of a disk with radius r is pi r squared, okay? And that's it. We just derived the area formula for a disk. Now, why did I do that? Like, what did we do here, really? What we did is this. We had a shape, we had a region, and we had our basic shapes, okay, which are in this case triangles. And before starting this, we first computed the areas of these basic shapes, areas of these triangles, and then what we did is this: we have our big shape, and we approximate the shape from within and from outside via these basic shapes. As you can see, I created these polygons inside the circle and outside the circle. I created two polygons. One of them is contained in the circle, the other one contains the circle. And these polygons are made up of triangles whose areas I actually know. And then that allowed me to squeeze the area of my shape between two numbers. And then I took the limit, and then I got the exact same limit, which told me that, well, therefore the area of my shape is blah, blah, whatever that limit is. In next section, we're going to do the exact same thing, except we're going to do this to a region which is the region under the graph of a function over an interval. And instead of triangles, as my basic shapes, instead of triangles, I'm going to use rectangles, okay? And we know the area of a rectangle. So we're going to do that. Instead of the expression you see over here, I'm going to have what will be called as upper Riemann sums. And instead of the expression here, I will have what will be called as lower Riemann sums. And I'm going to say that if my upper Riemann sums and lower Riemann sums, they approach to the same number, that number has to be my area, and that will be actually called the definite integral of a function over an interval. Okay? So that's that. I hope at this point you understood why I bothered talking about this, like why I bothered recording a video for this section, which I called auxiliary. Well, it is auxiliary, but it's actually a very good motivation for the definition of definite integral. And yeah, that's that. So expect more videos. Stay safe.